Okay, guys. This is trial two, by the way. You guys just will never know that, except for my saying that. I apologize for the delay in getting this recorded, but here it goes. So, the I have a devotional for you guys to start off because this has sort of been my life lately. Embracing obstacles. So it comes from James 1 2 through 3. It says, "Consider it pure joy, my brothers and sisters, whenever you face trials of many kinds, because you know that the testing of your faith produces perseverance." For years, I have viewed health issues, career setbacks, and other difficulties as frustrating interruptions to the life I wanted. Every time I overcame a tough situation, another one sprang up, slowing my progress. However, God helped change my attitude towards such challenges through an unlikely sport, dog agility. For over a decade, I ran alongside Portuguese water dogs through winding courses filled with jumps, tunnels, and other obstacles. In agility competitions, speed is less important than successfully navigating each obstacle. Both in dog agility and in life, I have learned that what is most difficult can prove most important. And thankfully, we do not endure trials alone. Today's reading from James teaches us that perseverance is developed through the testing of our faith during life's trials and is key to making us, quote, mature and complete. It also reminds us that God's guidance is available to all who seek it. Much like my dogs could master difficult agility courses when they sought my direction, I have discovered that I can better handle challenges when I direct my attention towards God. When we keep our focus on God, we can find joy even in life's most unwanted interruptions. Let us pray. Dear God, help us to see our difficult circumstances through your eyes, knowing that our struggles can help us to grow to be more like Jesus. Amen. So, it's been a challenge to record anything right now. But I'm here, yay! Okay, so take two of all of this. We talked last time about the Coriolis effect and how the Coriolis effect is a result of the Earth's rotation. So objects that are moving over the surface of the Earth, being currents, winds, or airplanes, missiles, whatever, while they're traveling, the Earth is rotating underneath us. And so as a result, we have things appear to be deflected. And so, sorry, we're going to talk a little bit more about this, but more in mathematical terms, which I know is not what you guys like. And, it's not what I like either, but it's just the way it is. Ooh, it imported slides I didn't want. We're skipping those. Let's get to the slide. This one. Okay, unfortunately, I cannot figure out how to not have it cut off from this one slide. All the other slides are fine, not this one. So, this is called, the first equation here, FCE, is called the Coriolis equation. So FCE equals 2W sine, and then this wonderful little symbol here. So W equals the rate of the Earth's spin. If this actually would behave itself, you would see that. But so this is an N here. I will do the blue. And so the Earth spin, just so you have a number here, which if you look at the slides that are already on Canvas, you'll see what the number is. But just so you have it here, this is 7.92. Oh, hold on a minute. Let me erase that. I missed a number. Eraser? Okay. Okay, 7.2921. times 10 to the minus fifth rads per second. Okay, rads is a way of measuring a spin. Okay, and then so this is 2 times the rate of the Earth's spin times the sine of the latitude. Okay, and so this equation tells us how important is this Coriolis effect. So let's see. For the rate of the Earth's spin, if you'll remember, if sine 0, so that's at the equator, then this is going to be 0. Okay, that's going to be your number. So sine of 0 equals 0. So 2w, whatever that might be, could be 2 times 2 million. Doesn't matter. Well, there's the rate spin. Earth doesn't spin that fast. But 2 times our Earth spin is going to be 0. So the Coriolis effect is 0 at the equator. If we have a sine of 90, that equals 1. So this is at the poles, and this is the largest number that you're going to get. The Earth spin is constant. It's not going to change here. If you go to another planet, of course it's going to be different. But we're on Earth. We only care about this planet right now. So this is the largest number you're going to get. So therefore, the greatest impact is going to be at the poles. And I'm running out of space here, so I apologize. Okay. So you will need to be able to answer simple questions using this, understanding the basics of the rate of the Earth's spin is a standard number. The latitude here, as you're moving from the equator to the poles, the force of the Coriolis effect is going to become greater. And I said force, I'm sorry. The effect of the Coriolis effect is going to get greater. Okay. So, if you look at the slide, you will see that there is a, just going to give me, I'm pausing you for a second. Okay, guys, so I added a little thing here. We have a little whiteboard here. Normally, if you look at the slide on Canvas, there's more to the slide, and I wanted to be able to write that out for you guys. So, here we have what is referred to as a Rossby number. And so the equation here is R naught equals U over FCEL. U is velocity. L is the length of time that an object, and I'm not writing in a straight line here, is in motion. We've already talked about FCE, so you have to have the answer from the previous question to be able to do this. And so this can be used to determine how important the Coriolis effect is. So if my Rossby number is large, then inertial forces dominate. Okay? And Coriolis really isn't all that important. If, oops, hold on a minute. Make it go away. If my Rossby number is small, then Coriolis dominates. So if Rossby is large, um, then you're going to have um, things like friction is going to be more important. Okay. Um, but anything dealing with rotation, then my Rossby number is going to be small. So if we look at this for you, the faster the velocity, the greater the Rossby number, and the smaller the Coriolis effect, so the less the deflection. And that seems to be a little bit the opposite of what we had talked about before, because we talked about the fact that as it got faster, it would increase in its ability to, Coriolis would become more important. But what really is controlling it is not just the speed, but the length of time that an object is in motion. That's really the bigger thing. The longer it's in motion, the more time the Earth is going to be rotating under it, and therefore the bigger the impact is going to be. Okay? So what's really important is how long is it in motion. And so that's going to be a relationship between U and L. On an exam, you may be asked to calculate Rossby number. Now, all the equations that we're talking about right now, they are going to be provided on the exam. There'll be a little equation list at the end of the exam, so you can go there and you can see, oh, here's this equation, this equation, this equation. They're not labeled. They don't tell you what all the symbols mean or anything like that. So you have to be able to just pick the equation out and use it. Sometimes you're just going to be doing a thing of like, if so if you're calculating the Rossby number, if you increased the length of time that an object is in motion, so you're increasing something on the bottom of this equation in the denominator, then the Rossby number is going to increase or decrease. So if L is going to be getting bigger, Rossby number is going to decrease. Other times you might be asked to actually solve the equation, okay? So make sure you bring a calculator with you to the exam. I usually only do about, on this particular exam, anywhere between 1 and 3. I don't remember what I put on the exam. I mean, it's written, but yeah, I usually do between 1 and 3 where you actually solve the equation. Otherwise, it's just looking at the equation and figuring out what the answers are, okay? And bring questions on this to the meet, our review session later today. So some implications here. For a bullet, U, our velocity is very large. Okay, bullets are moving very fast. So the deflection would be very small. And the travel distance is small. So deflection is pretty insignificant unless you're a sniper. It's a longer distance that you're traveling. And at that point, it does start to become a little more important. For an ocean current, the velocity is relatively small, not very fast, but the distance is really great. So deflection can be relatively significant. In tornadoes, the Rossby number is actually really large. They don't last for very long. They're fast, but they're really small. But in large low pressure systems, like the hurricane that people are watching right now, Hurricane Lee, the velocity is relatively high, but the length of time that's in motion is much larger. So what happens is your Rossby number becomes very large. In oceanic systems, it pretty much maxes out at the Rossby number, which is pretty close to 1. So for tornadoes, Coriolis effect is not very important. It's really a balance between what's called the pressure gradient idea that we talked about earlier, what starts the wind, and centrifugal forces, which are helping it to spin. In low pressure systems, centrifugal force is actually relatively negligible. And the balance is really between the Coriolis and the pressure forces. In the oceans, all three of those things are really important. The pressure forces, the difference in the pressure values, those are really important. The centrifugal force is really important. And the Coriolis force are really important. So there's a nice balanced system in the oceans, which is why I love the oceans. And we already talked about that, so whatever. So, any questions, guys? Okay, so I'm going to pause this for a sec while I switch to the next slide. Okay, I'm hoping this is all working. I'm not really sure yet. Let me see if I pause it. Okay, I'm going to say it's working, even though I'm not convinced yet. Okay, so now that we've had our conversation about all of this, we're going to talk a little bit about the Ekman spiral, which is a little bit different. We need a history lesson first, though. So we're going to go back and discuss Fridtjof Nansen. Let's see. Well, that should be a T there, not an F. It doesn't really. I'm making it worse. Okay. It really is Fridtjof. Fridtjof Nansen. So we have Fridtjof Nansen. He was from 1861 to 1930, and he was a very interesting individual. He sort of was a jack of all trades. He did everything. He was a Norwegian explorer. He was a scientist. He was a diplomat. He was a humanitarian, and he was a Nobel Peace Prize laureate. He contributed a lot to the development of modern oceanographic equipment, and he established modern theories in neurology while studying the central nervous system of lower marine organisms. So he read the theories of Heinrich Mann, that a current flowed east to west across the Atlantic Ocean and perhaps over the pole itself. And he based this off of artifacts found off the Greenland coast from a ship that was called the USS Jeannette. And this is particular ship is going to be discussed multiple times in here. That's 2 N's, by the way. Why can I not write normally with this little thing here? Yeah, that's better. Jeannette. So the USS Jeannette sunk off the Caribbean coast, and then pieces of it showed up in Greenland. So it sunk right here, and pieces of it ended up way over here in Greenland. So way over there in Greenland. And so people started thinking, well, there must be some sort of a current that's pulling everything this way. And so Nansen had this great idea, and you may think he's insane, and yeah, I'm okay with that. But he thought if you grounded a ship purposely in the ice, I mean, you embedded it in the ice. Most people don't want to do this. In the same location as the Jeannette, you would eventually drift to Greenland, and that previous attempts across the Arctic failed because they're actually fighting a current. So what he wanted to do was to take a small, strong, maneuverable ship with 12 men and provisions for 5 years. I'm not lying here. 5 years, and test this theory. Okay, so we're going to purposely run our boat into a ship, get it stuck there, and let it just float for 5 years and stay on a ship for 5 years straight. Okay, you understand the insanity to all this. So he designed a ship called the Fram. And Fram means forward. And he picked for his captain Otto Sverdrup, and that's a U, not an A, just so you know. It's a U. And once again, I'm making it worse. Here, let me see if I can erase it without erasing too much stuff. Ooh, oh, getting better. There, Sverdrup. Now, mind you, Otto Sverdrup later does a whole bunch of other oceanographic stuff. So he's got a really good group hanging out here. So that's what he did. If you look at our little figure here, we have our red lines here. I'll switch over to red. So I have my red lines here. And this is the trip that they took. Okay. I don't know why there's so many little weird curly cues, but this is his little trip that he took. This red portion goes from July to September 1893. So this blue line that you see here as they're moving along, so they're coming from here and they're moving pretty much all the way over to here. This is during the time that they drifted. And so this runs from September 1893 to August 1896 for about 3 years. There, floating. Now, mind you, they probably are going a little stir crazy by this point in time. The green line here, so notice I've got this little green line right here. So this is a trek that Nansen and one of the sailors did to try to reach the North Pole. So they tried to get up to the North Pole. Obviously did not make it. Well, actually, sorry, it started here and it goes this way. So they did not make it to the North Pole. They made it to 86 degrees, 13.6 minutes north, so close. And then they made it to Franz Joseph Island here, where they were rescued by a group, and so the purple line is their trip back home. This yellow line here is where the ship broke free from the ice. So at this point, they broke free from the ice and it continued its way back to Norway. Early on in the expedition, though, Nansen and Sverdrup noticed that the surface currents and the icebergs were deflected 20 to 40 degrees to the right of the wind. Okay, so they're realizing the wind is blowing in one direction, the ice is blowing in a different direction, and the current's in yet a different direction. So this came up of, okay, so how exactly does this happen? Like, why are the currents doing one thing, and I need a much bigger. This is not big enough. Let's see. I really wish I had a bigger eraser right now. Okay, I really need some space up here. So people started asking, like, what is going on here? Why are the winds going in a different direction than the currents, which is going in a different direction than the ice? And so it was first described by a man called Von, V-A-G-N, and then W-A Walford. Oh, wow. Okay, let me erase this. Wilfred Ekman. Okay. And that was in 1905. He was still a student. By the way, my major professor says that everyone's best work is done while they are still a graduate student. So he was still a student, and he explained that it was actually the result of a balance between frictional forces. Okay, so the friction between the wind and the ice, the friction between the ice and the current, and the Coriolis effect. And so let's do a little background here so we can understand this a little bit better. Whoa, everything got like thrown on top of each other. This is fun. It's okay. We'll make this work. Yeah, things are, I said, keep the scale. It did not keep the scale. It's fine. So the ocean consists of horizontal layers that move in what is referred to as laminar flow. So if we look at what we have here, this is laminar flow. It's the movement in layers where each layer does not really interact much with the layer below it. Okay. I'm a weird person. I, for some reason, have an obsession over faucets. So there are some times when you turn on a faucet and you can hear the flow of the water coming out. It's turbulent. And even though it comes mostly straight down, there's bubbles that are in there. But then there's other faucets that will have everything coming very straight and quietly. And that's because all the water is coming straight down. It's a laminar flow. Totally different sound. And that's the way the oceans are. The oceans are generally laminar flow, especially as you get below the area where the wind is penetrating. So if we think, and this is very simplistic, let's say we have a slab of ice and the wind blows over the ice. So I have a piece of ice here, and my wind is blowing in this direction. Here's my wind. So the wind is going to go here, and as the ice starts to move, it becomes subject. So my ice, this is the initial ice, and this is a result of friction. So as that ice starts to move, what's going to happen is Coriolis comes in, and it's going to deflect things to the right. I'm in the northern hemisphere, so it's going to deflect things like this. Okay, so here's my Coriolis. So the actual movement of the ice, sorry. I'm not sure what I had going here, but it's okay. Oh, wait. This is it. Oh, hold on a moment. Yeah, that's not it. It's not letting me erase things. I don't want to erase things. There you go. So I'll get this eventually. So the Coriolis is going this direction. It's going straight down. So the resultant movement is like this. Okay. I have my wind going a different direction here. It's fine. So this is the actual movement of the ice. So it actually goes, if I looked at this, about a 45-degree angle. And this is a very simplistic example. Another thing I want to note here is surface currents that are created by wind. They move, so the currents, move at about 3% of the wind speed. So it's a pretty small amount. So if I have, say, I'm running out of space. I want a bigger one. I need a little space here for my equation. So let's say I have a 20 knot wind. Okay, so if I have a 20 knot wind and it's going at 3%, so 0.03, because that's 3%, then my current is going to actually only move at 0.6 knots. Okay, and make sure you understand how to do that equation. It may also appear on your exam. Okay. Okay, so let's look at our Ekman spiral here. So this is what happens when a persistent wind blows over an extended area of the ocean surface in the northern hemisphere. Okay, I have to put the northern hemisphere in that because things are deflected to the right here. So what it does is it causes a surface current that experiences the Coriolis effect. And remember, the Coriolis effect is a force that is 90 degrees to the wind. So as a result, the surface current is going to move halfway between the force of the wind and the effect of the Coriolis, so about 45 degrees. So if we look here, we're going to look at just the surface here. I have this big arrow here. Okay, these are vectors. So I don't know how much of physics you guys have had, but in the idea of vectors, our vectors are done in such a way that the size of the arrow depicts how much force is going behind it. So my wind is my biggest force. It has the greatest speed, and so therefore it's going to be the biggest arrow. And then it also has direction. So I don't know if you guys watched the, what was it? Despicable Me, but vector with force and direction. Okay, so I have force, the size of it, and direction. It's pointing in a specific direction. So this is my wind here in the blue. 2 is my red. Red is the force from friction. And so friction is going to be in the same direction as the wind. So here's this one, which you can't, I'm trying to draw on here, but here, yeah, okay. And then you have the Coriolis effect, which is 4, which is in yellow. So this is my Coriolis effect. It's going 90 degrees. And then I have the resultant direction of the water, which is halfway between the two. And I'm going to draw this in green just so it stands out. Okay. So this piece here, this movement of the surface water, is going to have a little bit of an impact on the what's below it. This is going to act sort of like the wind. It's going to be that force of the friction. So if we look at the layer below that, I just muted myself. If we look at the layer below that, we see that this is now going to be our friction. Okay, because that's going to act as a little bit of a friction on the layer below it. And so Coriolis is going to be 90 degrees to the right. So it's going to go here. And so the water below that, okay, the water below that is going to go in this direction halfway between. Okay, you see what we're doing here? So this is going to be the force of the friction below. It's going to be that movement that's going to force the next layer to start to want to move in a specific direction. So here is for layer 3, it's going to be going in this direction. I have the Coriolis 90 degrees to it, and the water is going to move like this. Okay? So as you can see, we end up with a spiraling effect. Each layer is going to be the friction for the layer below that. And so as you can tell as we're getting down here, my arrows are getting smaller each time. So at the top is going to be my fastest movement, and at depth is going to be my slowest. So it gets slower as it moves down because it's losing a little bit of that energy each time. A little bit is being lost to heat. At the bottom, the current goes to 0 and is traveling in the opposite direction. And this is really important. Here is the movement of my wait, no, that's not right. Hold on a moment. It's going the opposite direction. So it's moving this direction. Okay? So it starts here and it spirals only 180 degrees. It's different from a tornado. If you look at a tornado, the tornado goes whoo, and it just circles around. In an Ekman spiral, if it was just start here and go this direction, it would only go to here and it would stop. It's not going to go any further. So, I can have like a big one here, and then the next layer, and the next layer, and the next layer, and the next layer, and it stops. Okay, it never does more than 180 degrees. It's limited on that because it just runs out of energy. Okay? So that's an important thing to note. The depth to which the Ekman spiral penetrates is really determined by how turbulent the water is mixing at the surface. If you have a lot of waves, this isn't going to work very well because it's going to mix everything. You really need to have a slow, steady wind. It is best determined in polar regions because the surface waves will destabilize it. Okay, next slide. Yes, I'm serious. So this is one example of documentation. So here we have this little boy here. Oh boy, I know, I can't say this word to save my life. I can't tell you how many years of speech therapy I had as a child, and I still cannot say this word. But this was mounted off of the coast of Bermuda, and it was there for 160 days during the summer of 1982. And what they did is they put devices to measure the movement of the water. Okay, so these are 80, no, they didn't do ADCPs. They put current meters. And all of these different depths. So they had one at 5 meters, one at 10 meters, one at 15 meters, one at 25 meters, one at 50 meters, 75 meters, 100 meters. Okay? And then it was attached to the bottom with a weight here that held it in place. And this is what they found. So this is showing the direction of the wind. I'm going to have the wind, in this color. So wind. And once again, these are vectors. So how long they are is telling me how fast it is. So as you can tell here, these arrows get smaller as you get deeper. So the speed decreases as you go deeper into the water column. And you can see from this that the 5 meters depth, the water is moving at about 45-degree angle here. See? And then you have 10 meters, 15 meters, 25 meters. It fell apart before it hit 50 meters. So we never got the full spiral, but you can start to see that spiral forming here. So they found this once over the course of 160 days during that summer of 1982. So in conclusion, they found that most of the surface current was restricted to approximately the top 25 meters of the water column. And they didn't think that it extended any deeper because it was summertime and the winds were pretty weak. There are no hurricanes or anything like that going through. Okay, so let's take a moment and talk about something closely related. So this is the Ekman layer, or Ekman layer / Ekman transport. So this is another way of being able to depict it. So we have these vectors here. You notice that they're getting shorter over time. And the Ekman layer is this layer right here. It's the surface layer. Oh, wait. Yeah. I'm not going crazy. So this is our Ekman layer. So it's the result of the wind itself and the balance between the friction from the wind and the Coriolis effect. So whenever you see a spiral, the Ekman layer is always this one. It's always the surface one, okay? So they're very much, these are just specific parts of an Ekman layer. It's not always observed because of waves, and it generally only extends 5 meters or so. Occasionally, if you're in polar regions, it might be 10 to 20 meters, but most of the time it's not that deep. Then there's also a concept called Ekman transport. If you integrate all of these vectors, in other words, you add all of the vectors up. So this vector, this vector, this vector, this vector, this vector, this vector. If you add all the vectors up together, you get Ekman transport, which is what we refer to as the net transport. So along this entire column, this whole thing, what's the average direction that the water is moving in? That's what it comes down to. And so the Ekman transport is always 90 degrees to the wind. So this is my wind here. So this is my Ekman transport. Okay. So in this is my movement of the water. This is my wind would be going here. This is wind. So 90 degrees to the wind is my Ekman transport. So what's the average movement, the transport of water within the spiral? Okay. Next slide. Almost the last slide. We're getting close to the end. Not sure why this extra stuff is back here. I'm not going to need it. So, we're going to talk a little bit about something referred to as geostrophic flow. So this is a special case. So if you have winds blowing one direction in one area, so this is my wind here, and in the opposite direction next to it. Based off of Coriolis effect, the net transport, so the average movement of the water is 90 degrees to the movement of the wind. So if all my water ends up here, what I end up with is a mound of water in between these two currents. And this happens along the equator. There are two wind patterns. They're moving in the opposite direction on either side of the equator. And as a result, you get a mound of water. Not in the equator. My bad. This mound ends up at 30 degrees because this is what's occurring somewhat close to the equator. I want to say close-ish. And that's not the right word. To the equator. And this is happening around 45 degrees north or south. So around 30 degrees, you end up with this mound of water. So when you go out into the ocean, all the water isn't mounded up there necessarily. There is a mound, but it's not a huge mound, and it's not continuously getting bigger. So what is going on here? So that is where you end up with the idea of geostrophic flow. So here's my mound of water, and later we will talk about this mound of water. So I have a mound of water here. It's higher in the middle. And I just noticed that my equations here are cut off too. That's fine. So gravity is going to try and force this water down. Coriolis is going to try to force everything up. So what happens is the flow of water is actually going to be like this. It's going to travel along here at an angle to everything as it tries to balance everything out. So we had some equations down here. They've been cut off, and I did not realize that these ended up getting cut off. But you at least have what some of my pieces are. So one of these is a function of u equals, and I've got to try and figure out how to piece this one together. So, I think, if I remember correctly, this is I forget now. Yeah. So this is not an equation you will have to answer anything on because it is something like that. Anyway, I don't think this is right, but this is a derivative. So it's a very much calculus based, so you'll never have to answer a question on it. But what I want you to understand is there are two things that are controlling everything. of what this current looks like. Its movement. So this one is a function of u, which is the force in the x-axis. There's another one here, which is a function of the force in the y-axis. And they're going to, so that's going to control how much it goes down here and then the over. Okay. So that's really going to control what kind of an angle this is coming down at. Okay. So the two of these together control what the flow is going to look like. They are controlled by fluid density. And so we've already talked a little bit about density. That's being controlled by temperature and salinity. And then it's also controlled by the change in the pressure gradient. So the pressure gradient is going to change. Remember, that's these lines here. So the closer together the lines are, the greater the pressure gradient. The further apart the lines are, the less the pressure gradient. So just be able to answer simple questions. This will be on the equation will be on your exam. And so you can say, as fluid density increases, this is going to increase or decrease. And whatever the actual equation is, not what I tried to remember from the top of my head. This understanding of pressure gradient, that the closer together these isobars are, the faster things move. That's an important thing for you to remember, because that's going to be really important later on. In the middle of the gyres, this mound can be about 2 meters higher than at the coastline. You don't see it while you're out because it's spread out over a really large area, but we have special satellites that allow us to see it. And this is actually going to be a really important feature later when we start talking about our currents. So you need to sort of keep that in mind. Because that will come back again later. Okay, so that is it for this lecture. Thank you guys so much for being patient with me. And I will record another one a bit later, but at least right now you have this one. So talk to you guys at 2:30 today. Take care, guys.